First, imagine you are watching a pot of water on the stove. There's a saying, "A watched pot never boils." Of course, this is not true in everyday life. The pot will boil no matter how much you stare at it. But in quantum physics, there is something similar that actually happens called the quantum Zeno effect. In quantum mechanics, when you continuously or very frequently measure a system, like checking whether an atom has decayed or changed state, you can effectively freeze its evolution. It is as if the system keeps being reset by your observation so it stays in its original state much longer than normal. This is like constantly opening the oven door while baking a cake. The cake might never finish baking because you keep interrupting it. But here is where things get strange and interesting. Under certain special conditions, instead of slowing down change, frequent measurements can actually make a quantum system decay faster. This is called the quantum anti-Zeno effect. To understand this, let us use another simple example. Imagine you are rolling a ball down a hill. If you keep stopping the ball and putting it back at the top, like constant measurement in the Zeno effect, it never reaches the bottom. Motion is frozen. But in some situations, if you keep giving the ball a little push each time you touch it, you might actually make it reach the bottom faster. In quantum systems, the same idea happens. If you measure the system in a certain way, instead of freezing it, the measurements disturb the system so much that they push it to decay or change state faster than it would naturally. Why does this happen? It has to do with how the system interacts with its environment, especially if the environment is dissipative, meaning it can absorb energy or cause loss, like a sponge soaking up water. In these environments, repeated measurements can open up more paths for the system to escape or decay instead of blocking them. A good question to ask is, how can simply looking at something make it decay faster? In quantum mechanics, looking or measuring is not passive. Each measurement slightly disturbs the system. In a dissipative environment, these disturbances add up, allowing the system to lose energy more quickly and making decay happen sooner. This is extremely non-intuitive because in our daily life, we expect observation to be neutral. We think that watching something does not change it, but in the quantum world, even observation can have a big impact. Scientists have actually tested this effect in various experiments, for example, using cold atoms or superconducting qubits, tiny quantum circuits used in quantum computers. By adjusting the timing and strength of measurements, they can switch between the Zeno effect, freezing up decay, and the anti-Zeno effect, speeding up decay. Why does this matter? Understanding and controlling these effects is crucial for quantum technologies. In quantum computing, for example, you might want to protect a fragile quantum state using Zeno effect, or in other cases, speed up certain transitions using anti-Zeno effect to make operations faster. In short, the quantum anti-Zeno effect shows us that in the quantum world, even the simple act of observation can have surprising and paradoxical consequences. Sometimes freezing motion, other times pushing it forward faster than ever expected. It challenges our basic ideas of cause and effect and shows how deeply different quantum mechanics is from our everyday experience. The quantum Zeno effect describes a phenomenon where frequent measurements can inhibit the evolution of a quantum system. It originates from the peculiar nature of quantum measurement, where each observation collapses the system's wave function. Repeatedly projecting the system into its initial state effectively freezes its dynamics, preventing transitions to other states. This effect has been experimentally observed in atomic, nuclear, and optical systems. The name comes from Zeno's paradoxes in philosophy, where motion appears impossible if continuously observed. In cold atom experiments, frequent laser probing can prevent atoms from changing their internal state, like constantly checking on a cake in the oven and stopping it from baking every time you open the door. Continuous measurements stop evolution. Contrary to the Zeno effect, the anti-Zeno effect refers to the acceleration of quantum state decay due to frequent measurements. Under certain conditions, instead of freezing dynamics, frequent observations enhance transition probabilities. This paradoxical result emerges from the subtle interplay between measurement timing, system-environment coupling, and energy uncertainty. The anti-Zeno effect requires the measurement intervals to match the characteristic timescales of the environment-induced transitions. As a result, decay or dissipation is accelerated rather than suppressed. In some quantum dots, carefully timed repeated measurements can increase electron escape rates. Like stirring a cup of tea more frequently to help it cool faster, repeated measurements can push a system to change state more rapidly. A dissipative environment is one in which the system continuously exchanges energy with surroundings, leading to decoherence and relaxation. In quantum systems, coupling to such environments induces spontaneous decay and loss of coherence, naturally favoring transitions. When frequent measurements are introduced in these environments, they can interact with these natural decay channels. Instead of suppressing decay as in isolated systems, measurements can align with environmental dynamics to promote faster decay. This interplay explains why the anti-Zeno effect is often prominent in strongly dissipative regimes. Superconducting qubits coupled to lossy resonators show accelerated decay under repeated weak measurements, like pushing a swinging pendulum at exactly the right moments to make it lose energy faster and stop sooner. The outcome, Zeno or anti-Zeno, critically depends on the interval between successive measurements. Extremely short intervals tend to freeze the system, Zeno, while intermediate intervals that resonate with decay processes enhance transition rates, anti-Zeno. This behavior can be predicted using survival probability calculations and spectral density analysis. The energy-time uncertainty principle plays a key role by allowing more decay channels to open during these intermediate intervals. Thus, carefully tuning measurement timing allows one to control quantum dynamics precisely. In atomic systems, adjusting the timing between laser pulses can switch between suppressed and enhanced emission rates. Like clapping at just the right rhythm to either calm or excite a crowd, measurement timing dictates the system's fate. Frequent measurements broaden the energy level of a quantum state due to the energy-time uncertainty principle. This broadening makes additional decay channels energetically accessible, allowing faster transitions. In environments with a dense spectrum of states, this increased overlap significantly enhances the decay probability. The anti-Zeno effect thus emerges naturally when the broadened state matches available environmental states. This theoretical framework is essential for designing experiments and controlling quantum devices. In nitrogen vacancy centers in diamond, broadening induced by microwave probing can lead to faster relaxation to the ground state. Like loosening a tight knot so more threads can slip through, energy broadening opens paths for decay. Numerous experiments have demonstrated the anti-Zeno effect using different physical platforms. Superconducting circuits, trapped ions, and cold atoms have been manipulated to observe enhanced decay under controlled measurement schemes. These studies often require precise engineering of the system-environment interaction and careful calibration of measurement frequencies. The results provide not only fundamental insights into quantum measurement, but also practical tools for quantum control. Such experiments highlight the counterintuitive nature of quantum mechanics, challenging classical intuitions about observation. Experiments with rubidium atoms in optical cavities show enhanced spontaneous emission under periodic probing. Like watering a plant too frequently and causing it to wither, excessive attention can hasten a quantum system's decay. The anti-Zeno effect is modeled using non-Hermitian Hamiltonians and time-dependent projection operators. Survival probability functions quantify how likely the system remains in its initial state after repeated measurements. Environmental spectral densities are incorporated to predict which decay paths are enhanced. These models bridge open quantum system theory and measurement-induced dynamics, forming a comprehensive theoretical foundation. They also inspire new ways to exploit measurement as a tool for quantum state engineering. Using the Leaf-Hughes model, theorists predict decay acceleration in atoms coupled to a broad continuum of modes. Like predicting how a fragile vase will break if tapped repeatedly at specific intervals, models forecast system decay under measurement. Understanding and utilizing the anti-Zeno effect has significant technological implications in quantum computing and quantum sensing. Controlling decoherence and decay is critical for maintaining coherence and fidelity. By deliberately employing the anti-Zeno effect, engineers can quickly reset qubits or force rapid transitions when needed. Conversely, avoiding unintentional anti-Zeno regimes prevents undesirable decoherence. Mastery over these effects enhances the robustness and versatility of future quantum devices. Fast qubit reset protocols in superconducting processors exploit the anti-Zeno effect to prepare qubits for new computations, like pushing a button to instantly clear a chalkboard. Controlled anti-Zeno dynamics allow rapid system cleanup. The anti-Zeno effect challenges our intuitive notion that observation always inhibits change. Instead, it reveals that measurement can act as a catalyst for transformation in quantum systems. This duality deepens our understanding of the observer's role in quantum mechanics and the delicate boundary between classical and quantum realities. Philosophically, it underscores the active role of information acquisition in shaping physical evolution. By studying this paradoxical effect, scientists explore profound questions about causality, control, and the nature of reality itself. The anti-Zeno effect illustrates that watching a quantum particle can sometimes make it disappear faster rather than keep it still. Like a performer who becomes more frantic under constant audience applause, quantum systems can rush to decay when repeatedly observed.